Hello everyone, and welcome to Comprehensive Rocket Science. My name is Rob Roundtree. So today we're going to be talking about how to calculate the true anomaly of your spacecraft when you have time since the spacecraft passed the perigee, you have your period, and you have your semimajor axis. That's not as easy as it sounds, and we'll talk about why that is in a minute, and get into the equations, and then show some modeling as well in Python and Excel of how you can calculate your true anomaly based on those few factors. Other thing I wanted to say is it's been a while since I put out a video. I just want to apologize. I've been pretty busy, but I found a good technical topic. This is something that hopefully should be a quick video and something to help people. So with that, let's get started. All right, so let's dive right into it. As discussed, today we're going to be finding our true anomaly from our time since perigee passage. Now, if you look here on the right-hand side of the screen, you can see you've got variables required for this are going to be your semimajor axis, your period, the gravitational parameter of your central body, that's mu, and the time since perigee passage, obviously. When I say t here, I really mean you could either have time since perigee passage, or you could have the time that you passed your perigee and the current time, and that, of course, will give you time since perigee passage. So, couple equations here. So you can see first one, the period's equal to 2 pi times the square root of your semimajor axis cubed divided by your gravitational parameter. That gives you the period. That's a pretty common equation. You see that quite often in orbital mechanics. It's a pretty basic one. It's derived from Kepler's laws. Ideally, I'd be able to derive that, but this is a short video, so I'm not going to do that right now. I'll make another video to do that in the future. The other thing you have, so once you have your period, that's going to tell you a couple things, right? So this n down here, mean motion, that is the best way to explain this mean motion and mean anomaly is if you, instead of having an eccentric orbit, so we'll go over to the board. So, the situation you have here, let's say this is Earth, right? We're talking about, a spacecraft with an eccentric anomaly, an eccentric orbit. So this is obviously, that's your apogee, or your highest point of your orbit, and this is your perigee, right? And Earth is in the middle. This is Earth right here. So, what happens is you end up going faster down here at your perigee, and as you approach apogee, you're getting further away from Earth. Earth is slowing you down, the same way that, a ball slows down when you throw it uphill, when you throw it up. So, your spacecraft's going to be moving a lot faster down here than it is up here. As a result, that's going to cause you to pass through this area a lot faster than you pass through this area up here. And you can't just calculate where you are in your orbit based on how long it's been since you passed your perigee, unless you have a little more information. So what the mean motion is about is, so say, all right, this is Earth here. Now, instead of there's a bad circle, but you get the idea. That's supposed to be a circle. Now, instead of having an elliptical orbit, let's pretend like this orbit is a circle. So what that's gonna do is now, really, you don't have any such thing as your perigee and apogee because it's a circular orbit. Perigee and apogee are the same. All altitudes are the same. But you can say that since you pass this time, or since you pass this point right here, you can call it the perigee or whatever you want. You know that your speed is constant throughout this entire circle. Your speed is constant. So mean motion, all that is if you were going a constant speed, so n is mean motion. If you were going a constant speed, I'm going to zoom in a little bit here. It's also going to make my writing better. If you were going a constant speed, your mean motion is going to be 2 pi divided by period. And this is really true. I mean, mean motion is the average of your speed throughout your orbit, right? So your orbit period is, say, I'm going to make something up here, say 90 minutes. So what is that? Let me grab a calculator. 90 minutes times 60 seconds. Math in public here. Was that 5,400 seconds or something? Yeah, 5,400 seconds. So you have 5,400 seconds equals your period. Now your mean motion is going to be how many radians you do in that period. So you're going 2 pi radians in a period of 5,400 seconds. So let's go ahead and do that calculation. 2 pi divided by 5,400, that's going to give us a mean motion of 0.00011,636 really, radians per second. So on average, on the circular orbit, that is how fast you're moving, right? Is you're moving 0.0011636 radians per second in the circular orbit. Well, so in this eccentric orbit, you're not moving that speed the whole time, but on average, that is the speed you're moving because your period is what it is. On average, you're moving this speed, 0.0011636 radians per second. So that mean motion is going to be an important parameter for us. Now, from mean motion, you can calculate your mean anomaly. Mean anomaly, this is where this circle becomes more important. Mean anomaly is, okay, if you had a circular orbit with the same, another assumption I should have said about this circular versus elliptical orbit is that they have the same A or semimajor axis, right? Otherwise, it's apples and oranges. And your semimajor A is obviously your semimajor axis, which is on the right-hand side. And let's say, let me think here. I think our semimajor axis, yeah, will already be calculated based on our period. So let's go ahead and calculate that actually. So semimajor axis, so P is going to be equal to 2 pi squared root of A cubed over mu. That's going to be up there on the top of the right side. So if we calculate, so then let's see, I'm going to do math in public again here. P over 2 pi squared, we've done this plenty of times, times mu, cube root of that. Cube root of that is going to be your semimajor axis. So we can go ahead and calculate that with a period of 5,400 seconds divided by 2 pi. We can go ahead and square that. And then multiply that, square that, multiply that times our gravitational parameter, which is 3.986 times 10 to the 14th meters cubed per second squared for Earth. That gives us 2.944 times 10 to the 20th. We're going to go ahead and take the cube root of that. That's going to give us A equal to 6.652 times 10 to the 6th meters, or A equals 6,652 kilometers. So really, this is going to be pretty close to a circular orbit anyway, because that you're so low here. This is only less than 300 kilometers in altitude, but we can go ahead and use these numbers just for fun, and I'll make the orbit slightly eccentric. All right, so we've got our A, and here you're assuming that in order to make this mean motion thing work, right, you have to assume that the A of your circular orbit, which is imaginary, and this your actual orbit, this ellipse, the A are the same. So we went ahead and calculated our A. Now, the mean anomaly is, that's going to be your mean motion times the time since apogee passage. That's all that is. So if you assume you're moving a constant speed, around this circle with a semimajor axis A, I'll go ahead and draw that, right? Semimajor axis is this length here, that's A, and for your elliptical orbit, that's A, or this entire orbit is 2A, right? So, you're moving a constant speed along here, your distance, your angle in radians that you've passed since, or that you've gone through since your perigee passage. That's just going to be equal to the time since you passed your perigee times your mean motion. So we have a mean motion of 0.0011636 radians per second, and equals that. And then we have a delta t, let's say it's been 20 minutes since we passed our perigee. So that's 1200 seconds since we passed perigee. So you can calculate your mean anomaly then as m equals n times t minus t naught, or n times delta t, which equals 1200 times 0.0011636, 1.39632 radians. That is this angle right here, this theta. That's the angle you've traveled through. So that's the angle you traveled through, like I said, on this imaginary circle right here, but that's not the angle you've traveled through in your eccentric orbit, because, like I said, you're going faster toward your perigee, so you're actually going to be a little bit further for your eccentric orbit. Likewise, if you had a mean anomaly that was greater than 180 degrees, then you'd actually be a little closer to apogee than you would think. In this case, you're going to be either way, you're going to be a little closer to apogee than you think, because you pass through perigee more quickly. So what you can do with that, and this is really where the problem starts getting a little more complex. So this equation here on the right, your mean anomaly equals your eccentric anomaly minus your eccentricity times the sine of your eccentric anomaly. Again, this is the sort of equation that I would want to derive if I had more time, but I don't. So today we're just going to take this equation for its face value, and we're going to say that m equals e minus e sine e. So a couple things here. One, this is a transcendental equation, so we cannot solve for this analytically. We must solve numerically, right? And there are a couple different methods we can solve numerically, and I'll get to those momentarily. Another thing that's worth noting is, so, we went through this step by step, and hopefully what was a somewhat intuitive fashion, right? From your period calculating, hey, this is, this is your mean motion. This is how far you would be on a circular orbit past your perigee, right? But really, from an equation perspective, you can skip all this and just come down here to say that your eccentric anomaly minus your eccentricity times the sine of your eccentric anomaly is equal to square root of mu over a cubed. Sorry, my writing is terrible. Times delta t. This is just combining those four equations we just did, but it's good to know where you're coming from, so you actually understand what's going on. Fix that. No, that's no better. Okay, well, maybe it's a little better. All right. So, like I said, this is something you have to solve numerically, and that is what we'll do in the next few minutes. So there's two ways to solve this. So you can either do, it's got to be numerically, obviously. You can sit there with a calculator and mess around for a while. Really wouldn't take that long, 10 minutes. You can probably get an answer, maybe using E equals M as a starting point, right? That's not the most intelligent starting point you could do, but it is a starting point. Since you have your M, you could just start with E equals M and then go from there. What we're going to do is go to Excel. You can use the goal-seek function in Excel to solve this. You can also mess around numerically in Excel. And then I also have a Python script that I wrote that you can use to solve this. So we'll cover those right now. All right, so we've got Excel open here. You can see that I've got a couple eccentric anomalies, which I'll explain, a couple mean anomalies, and then an eccentricity. One thing I realized that I forgot to bring up was that another thing you actually need for your for this is your eccentricity. Obviously, if you don't have eccentricity, you're not going to be able to find that. So that's added there. You can't find your M without it. So. All right, so for eccentricity, that needs to be given, as I stated. I just made this up, let's say 1. So we have our eccentricity equal to, 0.1. And that's going to be a nice low eccentricity that hopefully will make our perigee not below the surface of the Earth. Surface of the Earth, obviously, is 6378 kilometers. So we will see if this works out. All right. The other things I have here, like I said, a couple E's, a couple M's. So you enter the eccentricity, which I already gave. For M, we're going to go ahead and enter what we got here in radians, so 1.39632. That's what we got here on the left-hand side. Then we have this M guess here. This is going to be this is actually going to be the function we're trying to make equal to the M up above. This is calculated. It's calculated by doing this equation, basically, taking the eccentric anomaly that you give it and subtracting the eccentricity minus the sign of the eccentric anomaly. So that's that. So what you can do is use Excel and use the goal-seek function to cause this M to equal this M up here by changing this E naught. And I'll go ahead and show you that. You can also, you can mess around with this E naught yourself. If I make it 1.2, all right, M's a little closer to M guess. What about 1.4? All right, it's closer now, 1.45. So you can sit here and mess around with it until your M equals your M guess. This E1 will also equal E naught at that point. But the goal-seek function is really an easier way to do it. So this is Excel 2019, but I believe it's the same if you have 365. So you go into data, go to what if analysis, and then goal-seek. All right, so set cell. We want to set cell 9, or sorry, B9, right? The M that we're guessing to what value? We want to set it equal to this M, right? So we want to set it equal to 1.39632. Unfortunately, you have to hand type that in. And we're going to change what cell? We're going to change this E naught cell. And what it's going to do is iterate this E naught cell until that M guess cell equals the M cell. And like I said, this E1 should also equal E0 when it gets there. All right, we got the solution. Pretty good solution. Yeah, it's off by, I don't know, maybe a 10,000th place. So, you could manually get it closer at this point if you wanted to, but this is pretty good. So, it came up with a M of an E of 1.49611. And yeah, that's pretty much that. So that will give you your E, and from there you can go and use your next equation to find true anomaly. I'm going to go ahead and show the Python script to do this as well, because that's just another method you can use. All right, so now I've got Python up. I'll go ahead and make this a little bit bigger too. So this is what I got in Python. So we'll start with the eccentric anomaly file. So this file is actually going to find your eccentric anomaly based on the method that you pass to it. So you can see here there's a couple different ways to do it. Basically, You're defining the method, eccentric anomaly. You're passing it an array. You're passing the method, whether using Newton's method or whether you already have the true anomaly. And then you're passing it the tolerance. And that's going to be how close you want it to match to, how close you want M to match to the actual M that you passed in. So if the method equals Newton, which is the one we're going to use, the guessing method essentially, and we don't already have true anomaly, so we can't do that, we will use this Newton-Raphson method to iteratively find E. And just to be clear, I'll go ahead and expand this. Just to be clear, this doesn't exactly match the Newton-Raphson, but it's fairly close, and it's going to converge on a correct solution for E. So this array here that you're passing into the eccentric anomaly function, you're passing in the ME, which is just your mean anomaly. This is I got this. There's actually an excellent series of Python lectures online that I got some of this code from, or the variables at least. So I'll pass the name of that YouTuber down in the links, but he's excellent. So we have our mean anomaly, we have our eccentricity, that's the array that you're passing into this function. Next, you're going to iteratively solve for E. You have an initial E, and that you're going to initially set your initial E equal to your mean anomaly. And then you're going to iterate 200 times. In this example, you could change that number if you wanted to. Your guess for mean anomaly is going to be equal to that equation right there, right? Your E minus sine E, which is all this is. And then if it is within tolerance, if the difference between what you guessed and the actual is within tolerance, it is going to return the answer to the function that called it, which in this case was this true anomaly, called it. It's going to return that E into this file, and then I go ahead and print out the E, right? So all right, if it did not work, if it did not find it on the first pass, then it's going to set this E1 equal to what you had, and it's going to subtract what you had from the actual value and divide by 2. So it's just going to get a little bit closer. And from there, it will go ahead and set E0 back to E1, and that's going to pop you back up to the top here for this for loop, and it'll guess again. This is going to solve iteratively 200 times until you converge on a solution. If it doesn't converge in 200 times, it'll return false. And yeah, that's pretty much it. From there, like I said, you're entering your mean anomaly and your eccentricity. Mean anomaly is an M here, it is an ME here, just know that, but that doesn't matter. They're not referencing those parts of each other. And you're going to go ahead and set this E variable in this file to what you got from the eccentric anomaly, method. And you're passing it the M set right here. You're passing it the eccentricity right there. And you're passing the method, which is Newton, which is defined right here if method equals Newton, using the Newton-Raphson method or an approximation of that. And then we go ahead and print out E. So let's see what this looks like, what it comes up with. I'm going to solve it. Answer comes out down here. It came out with 1.49604. So let's take that, compare it to our Excel, 1.49607, or 1 is about what Excel came up with. This is probably better than what Excel came out with, so let's see. Yep, sure is. That matches just about exactly. So that gave us a better answer than Excel did. All right, that is that part of the Python script, and then there will be a little bit more to get true anomaly. All right, so the last thing to cover here is, now that we have our eccentric anomaly, how does that help us get theta? Well, let's take a look. So the eccentric anomaly we got was 1.4960407. I'll go ahead and paste that in here if I can figure out how to. It may take longer than we would hope. There we go. All right, that equals, equals E. All right, Pretty straightforward. So now that we have E, we need to find our next equation, which is this one down here. Theta, that's our true anomaly, we're going to find from this equation. So you can actually, just using the eccentric anomaly, you can find, and the eccentricity, you can find your true anomaly. So if you take a look at this equation, it's pretty complex, but it's not transcendental. You can actually simplify it, which I've done right here. Or by simplify, I mean solve analytically. So that's what you end up getting for your theta. So let's go ahead and solve that. True anomaly, and then I'll reference this one over here to make sure we don't mess anything up. True anomaly is going to equal to, you've got that that tangent of E over 2, right? You're going to, we're just going to divide that by square root of 1 minus E over 1 plus E, and then take the inverse tangent of that. And multiply this whole thing by 2. So you can do that in a calculator. You can do it in Excel, Python. I'll pull up the Python script I use in Spider. So I'll just scroll down a little so you can see that more in the center of the screen. So this is what we're going to use. Basically, you're passing the function your eccentric anomaly and your eccentricity as an array. It's gonna print that array as unnecessary. That was just for troubleshooting. It's gonna find your true anomaly using the equation I just created. It returns it back to this one, and then we can get it. So your true anomaly in radians is what's going to be passed by that function. Your true anomaly in degrees, you're just going to multiply by 180 and divide by pi to get degrees, and then it will print out your true anomaly in degrees. So let's do that. All right, true anomaly in degrees, we've got 91.4614 degrees. 91.4, what did I say, 416 or 46? We'll say it's 46. 4614, yep. Degrees. All right, and that is that pretty much. You can do this with a calculator. You can use Excel, anything you want really. Pretty easy there. So that was it pretty much. That is how you find true anomaly. Just to recap, so what did we need for this? We needed our semimajor axis. We needed the period, obviously the gravitational parameter of our central body. We needed the time since perigee passage, and we needed the eccentricity. But really, I mean, A, P, E, and mu, you're going to have all those if you know your orbit. That's just a couple parameters of your orbit, right? You can find some of those using other variables or each other. And then T is, the one thing you really need, your time since perigee passage. But pretty straightforward. Hopefully everyone followed this explanation. Let me know if you had any issues or if I messed anything up down in the comments. And otherwise, thank you so much for watching, and I'll see you next time. Thanks. All right, and let's talk about how this solution compares with our mean anomaly. So true anomaly, we've got 91.4615 degrees. Let's just fact check that against our mean anomaly. So our mean anomaly was what, 1.39632 radians. So times 180 divided by pi, that's going to be 80. Mean anomaly would be about 80 degrees, right? So does that make sense? Well, look back to our orbit and think about it. So mean anomaly, we've passed through 80 degrees, right? So that's just shy of 90. And in our elliptical orbit, we've passed through just over 90 degrees. So does that make sense? Well, yes, it does. You're going to pass your perigee faster, so you're going to go a little bit further through that perigee, which is going to get you over 90 degrees true anomaly. Versus your mean anomaly a little less than 90 degrees. So makes perfect sense to me. This seems like a reasonable number, and yeah, congrats on solving that. So, like I said, pretty straightforward. Just a couple things where needing to solve this numerically is a little different than what you have to do sometimes. So, thank you very much. One last thing I wanted to say: if you enjoyed this video, please like it and consider subscribing to the channel. That means a lot. If this is something that interests you, this is exactly the kind of content that I want to be putting out. I don't have time right now to be posting a lot, but when I do have time, I'll make sure to put in a technical video, something like this that's just short and to the point about a particular topic. My real goal with this channel is to make lectures that are almost university level in their detail and complexity and length. So if that's something that's interesting to you, if you want to learn more about the technical aspects of rocket science and how to actually do the math and learn the detailed aspects of this, please subscribe to the channel, follow me, and I'll be posting a lot of that. With that, that's going to do it for me. Thank you for watching Comprehensive Rocket Science. I'll see you next time.